Okay. So let's continue. So we got quite a lot of information from linear stability analysis. So basically, we found that we can find the critical point. We can find the critical value of Reynolds number. And Reynolds number is essentially proportional to the velocity, maximum velocity. Remember how we defined the Reynolds number? It contains velocity. It is proportional to velocity and specifically to maximum velocity. So the larger the velocity, the larger the Reynolds number. And therefore, the faster the fluid flows through the channel, the more likely it will become irregular, so something will happen to it. Instead of just being fluid flowing along the channel like in straight lines, it will start forming the waves. That's those waves that we just saw. So that is the typical example of transition. So from one solution to another. And the point where this happens is called critical point. That's why we call critical Reynolds number, critical wave number, critical speed. All these quantities which we can compute are called critical, right? Critical layer, all these is critical. And it turns out that critical regime corresponds to a certain wave. Remember, because when we consider the distribution of growth rates, sigma, with alpha, there is a maximum there. So therefore, the idea is, so all right, we have that maximum, and that maximum, the growth rate is positive. Means that perturbations will become larger and larger and larger. But I also mentioned to you that perturbations are not necessarily growing at a single value of alpha. So if I draw a sketch, sigma r as a function of alpha, then what we will get is something like that. So this is the maximum. So I'll call it alpha max. And the critical situation will be when we have this max just touching. This is critical regime. Right? So, but this is called supercritical regime. Okay? So, when the this sigma curve touches the horizontal axis, right, zero axis, that is called critical, and if we bypass that, then it is supercritical, above critical. Okay, so that means that this wave number, or wave with this wave number, with this wavelength, periodicity, will be growing in time. But then we will say that this wave number will also be unstable. So wave with this wave number, which is slightly to the left or slightly to the right, will also grow. Okay? So all of them will grow. And therefore, what we will get is essentially a so-called wave packet, when the group of waves between with wave numbers between here and here, they all will grow. All of them. Is that clear? Because they have positive sigma value. So they will all grow. Then the question is, again, always the same question. If they all grow, what exactly will we see in the experiments? And the answer is that even though they all grow, what you will see in experiments is the strongest one. And again, this makes common sense. If all of them grow, but some of them are stronger, well, they will push the rest out somehow. So therefore, what you will see in experiment is, even in this regime, you will see a wave which is predominantly has this wave number alpha max. Okay? So simply because it is growing faster. By the time it grows to by a factor, say, of 2, these ones will grow by a factor of, I don't know, 1.1. By the time these ones will grow to by a factor of 2, the first one, the central one, will grow by a factor of 8. Something like that. So it will always be larger than neighbors. Okay? Unless somehow you introduce very idealistic initial conditions when you say, well, all right, I have this diagram, but I somehow exclude all these from the initial conditions. They are not there. I will only introduce perturbation initial conditions so that it has periodicity corresponding to this wave number. That's what happened. In that case, you can say, all right, in that case, we will get some slower growth rate. But is it physical? Is it realistic? Again, coming back to reality. And the answer is no. You cannot control perturbations, initial perturbations. They are always absolutely random. Why? Because you're conducting an experiment in a physical room, and there are people in that room, and they move and they talk, and they sneeze and they cough. And they do it not in any programmed way, absolutely randomly. So therefore you cannot ever create the situation when only filtered perturbation of a wave number is excited. So you, in reality, you always should assume that all of them will be excited because you have noise containing all sorts of perturbations. Explosion somewhere, thunder somewhere, somebody sneezing, somebody talking, somebody walking, somebody running, birds are tweaking or something like that. All these are perturbations and they're always here. So here we have fans, we have air conditioner going, right? So I'm standing here and it squeaks under my feet. So all these are perturbations and they are completely uncontrollable. So therefore we always need to assume, if we want to be realistic, we always will be assuming that all initial conditions, the initial conditions are such that they allow everything to grow if they can grow. And in that case, it is just survival of the fittest. Brutal law of nature. So the strongest will survive. Same thing here. So even though we have this range, the strongest will survive. So therefore, this alpha max, sigma corresponding to alpha max, will give us what we will see in experiments eventually. Is that clear? So this physical argument leads us to the following mathematical simplification. So if we know that by physical reasons, from physical reality, that the strongest only will survive and it will dominate everyone else, so why don't we ignore everyone else from the very beginning? See the point? So we know that no matter what we do, no matter what sort of democracy we have here, well, dictator will always dominate. And dictator is this guy here. So therefore, that dictator will suppress everyone else. Right, let's focus on the dictator. So let's say, therefore, that my solution, full solution to the problem, so W is equal to, so I have W bar. That's my base flow. It is always there, so because it feeds everyone else, right? So, and then we will add perturbation, right? This perturbation that we introduced before, well, let me call it, just be consistent with our notation, so it's not prime. I will write it as hat, and it is of Z, but it is proportional to I alpha x. Okay? So this is my WZ, this is my dictatorship, so I will choose alpha which corresponds to this one. So, okay? So this is alpha that I'm choosing. And I'm substituting that. So it's alpha max, but I just don't want to put my alpha max index in, right? Because it will make it clunky. Okay? So I'll take this alpha max and I will stick it there, so but I will call it alpha. And the reason for that is just because I'm lazy. I don't want to write max, max, max everywhere. But that's what we mean. So make a note in your notes that we are using the maximum, this maximum amplification rate. Okay, so this is eigenfunction that we just plotted. We know how to compute it. This is the value of alpha which we can determine. And what else am I missing at this stage? Compared to what we had before. What else? Sigma, right? And I will tell you why I was not in a hurry to introduce it straight away. Because it is exponential term, right? It is an exponential term, and if sigma happens to have positive real part, it will grow forever. Exponential function, if it grows, it grows. It never stops. And if the perturbations are small, we can afford that. But since it is exponential growth, very quickly it will become non-small. And if it keeps growing, what do you think we would expect to happen physically? Like, if it is an object, physical object, for its existence or growth, we need to supply energy. Right? And energy is supplied by the base flow. But base flow, by default, by design, has finite capacity, right? So it is only as fast as the pump can make it, right? So if the pump, which creates this flow, creates the pressure gradient, is already at the top of its capabilities, we cannot get any more power into that, any energy into it, right? But if we say that perturbations grow exponentially, they don't know about those limitations. They will just keep growing and growing and growing. So, and this is completely unphysical situation. They cannot. Simply, we cannot supply that much energy. Is that clear? So therefore, I cannot really expect the exponential growth will continue forever. It cannot. Simply because we don't have enough energy. Energy supply is always limited. So therefore, I have to start thinking how I can modify my model, because my initial model is clearly insufficient. Okay? It has its limitations. We got what we got a lot out of it. What we cannot get out of it is so-called saturated state. We don't know how strong the final solution is. So remember, during the break I discussed, so we have this pattern, wave pattern, we impose, add it on top of the base flow, but we don't know what we're actually adding, so how strong it is. And I choose this coefficient which multiplies the eigenfunction to stick it in. Just arbitrarily, I said, well, let's make it 0.1. Well, why 0.1? Why not 0.2? Well, because it looks good, right? So therefore, what we need to do is to fix this ambiguity. And we know that amplitude, so the coefficient in front of that, cannot be infinitely large. It cannot grow exponentially forever. So therefore, I need to make sure that I will fix that problem. And what I will do, I will simply say, all right, I don't know how far and how long and how strong it's gonna be when it grows, but it will grow and it will not necessarily be exponential. So is that clear? So therefore this will be realistic rate, which initially is exponential growth rate, and then it has to level out. Just physically it has to have saturated value. So, and what the shape of that behavior is, I have no idea. So, but I know that it will change with time. So therefore I put this amplitude in A of t. Okay. So therefore my goal is to find this A of t. Why? Because I already know what that is. I started with that. I already know what that is. I found it. I know what that is. It is eigenfunction. I plotted it. That's the only thing which I don't know. Okay? Is that clear? So our goal from now on is to find this A of t. And that's the essence, and that's the final ultimate goal for weakly nonlinear analysis that I will be introducing next. Before we go there, though, there is one more thing we need to take into account. So this is a physical quantity. This is a physical quantity, right? So overall, this is a physical quantity. Physical quantities must be real. This is definitely real. This is a parabola, right? 1 minus z squared. We know what that is. However, this is complex. That's how we derived it. It was complex because that simplified our algebra a lot by having it as a complex. But can we live with the complex, just this complex bit? No, because that is supposed to be physically relevant result. In physics, everything is real. Okay? So therefore, we cannot just stick with that. We have to add complex conjugate. And what is complex conjugate of e to the power I alpha x? Just minus, right? Okay, so that's what we need. So therefore, if we have these two, if we add them together, then we will get definitely a real answer. So that's what we need to keep in mind. And what I will do, I will just write it by introducing better notations. So I introduced a capital E notation for exponential function, partial exponential function. So then this becomes E, and is it clear why it is E minus 1? It should be quite clear, right? So because I have minus there, so therefore it becomes just E minus 1. Okay, so it's literally 1 over. So, all right, so that's what our goal is. So now we know everything here except A. So we would like to know what A is. And we would like to know what A is in the long term when t goes to infinity, so when t becomes large. Okay, so that's our goal. Is that clear? Okay. Now, let's just see. Okay. Very quickly. What I suggest we do, I will switch to my notes now. So I will be displaying the notes. And once we get to some sort of fine point, I will switch back to notes and will write explanations on the board. But bulk of the notes will be displayed on the screen. So pretty much what you see here is a repeat of what I already explained. So that business with about maximum value and how we create the solution. So, and that is the solution. So that's the representation of the solution. I explained all that already. Here we go. So if we substitute this new form W bar plus W 1 1 and W 1 minus 1. So one more thing I didn't explain. So when I write W, I would like to introduce two indices. The first index will correspond to the power of A. See, A appears to the first power, so that's what you see here. The second one will correspond to the power of E, capital E. E to the first power, that's the second index. So therefore, what we will have, if we substitute these into our linear equations, we will get the linear equation which is written like that. Okay? If you substitute a sum into a linear equation, then it will be a sum of equations. So that's what I have here. So is that clear? So what I will get is obviously, I will not have sigma appearing anymore because I suppressed that e to the power sigma t term and replaced it with a. Instead, I will get derivative with respect to time. That's what I have. So x is still the same matrix as we defined before. Y is the same matrix as we defined before. And the only thing is that I suppressed the dependence on Reynolds number. It is there, but just to make it a little bit shorter, writing it a little bit shorter, I do not show it here. But we remember that it is there. So, but we also have that the second term, this is complex conjugate term. And for complex conjugate term, we will get its own system of equations. But because of linearity, to get this solution, so this equation solved, we just need to set this to 0 and this to 0. And as a matter of fact, if we solve these equations and take the solution and just make it complex conjugate, we don't need to worry about this. Is that clear? So formally, this is the form of the equation, but we only solve this one. And once we solve this, we take that solution of the first part and make it complex conjugate, and we automatically get the solution for the second one. So basically, that means that we will never need to worry about this explicitly. It will be just freebie. We solve this one, and this is going to follow. Clear? So complex conjugate part is never solved for. We don't need to solve for that explicitly. Okay. So that's the thing I'm saying here. And then the first important conclusion. If our equation looks like that, right, in a matrix form. So what you see that we have this bit here which does not have time derivative. It has a, which is a function of time. This part does not have a. It has derivative of a with respect to t. W11, we know it is not equal to 0. We saw it, we plotted it, right? So this is not 0, but the result is 0, which means that this whole thing must be 0, meaning that these two terms must balance each other and kill each other. that means that they have the same functional form. Otherwise, you cannot get them to 0. Therefore, dA by dt has to be of the same form as A, or in other words, dA by dt must be proportional to A. So you should remember these arguments. I already used them previously. 1-to-1, no change. I just repeated the same arguments once again. But it is important because these arguments will appear in a different context now. That means that I make a conclusion, logical conclusion, that this is proportional to that. And that's exactly what I write here. dA by dt is proportional to A. And the coefficient of proportionality is, surprise, surprise, sigma. Right? Why? Well, in this case, it's just, I happen to choose the same notation, but this has nothing, at this stage, logical stage, this has nothing to do with the growth rate. It's just a matter of matching two terms, pure matching. So they appear in the same equation. They have to have functional form, because otherwise we will be adding apples and oranges. And therefore, that's how it must be. Otherwise, we will not be able to balance equations. Is that clear? Nothing to do with growth rate or anything. It's just making two terms to add to 0. Nothing else. That's an important concept that we will be following through the rest of this subject. All right, so that's what that is. Of course, if I formally solve this equation, I will get my exponential solution. Here it is. So essentially, I got the same outcome as before, but following slightly different route. So this is a good thing, because we came from different points with different logic, and we converged to the same answer. So from here we will get this, right? So, but the important thing at this stage is not that. The important thing is this. This is the first step in deriving the amplitude equation. So from here, we deduce that the amplitude, the equation has to be of this form. It cannot be anything else, right? So no matter what sigma is, that the equation is like that. It cannot be anything else. Is that clear? That's the logic here. So, and it just happens, it's a freebie, it's a benefit of us knowing something about this equation, this type of equation, that the solution exists like that. But the outcome, the main outcome here is not that. The main outcome is this. Logical outcome. That's what we were looking for. So, and we figured out that A has a rate of change of A must be proportional to A itself. Cannot be anything else. Okay, so that's the logic here. And now I need to look at my equations more carefully. So what do I mean by that? Remember, we started our investigation with an assumption that perturbations have small amplitude, so A is small. It is so small that the product of A times itself can be neglected. That's essentially what how I remember. We said that U prime is small, and U prime times U prime is even smaller. But U prime is U hat multiplied by A. And out of those two, it is not U hat, but A, which is small, right? U prime is small, but U prime is A times U hat. U hat, we plotted it, we could see it, so it is not small. But the factor multiplying it, A, is small. So therefore, that's the second thing. So we assume that A is small. So this A is small, or this A is small. Well, so far so good. But if we claim that sigma is positive, and if we claim that because of that A will grow, well, it will not stay small. it will become finite, right? So how can it grow without not becoming larger, right? So it doesn't make any sense. So it is to grow, and if it is to grow, then it will become large. Okay. So again, that's the logic of it. Common sense, nothing about mathematics, right? So, but that's what it is. So, bottom line is that A might be small initially, but eventually it will be large. So therefore, when it becomes large, our equations that we solved, they will be insufficient. Why? Because, and I'm going back all the way, I don't know how many pages and how many lectures. Up to here, so it is page 9 in my notes. Look at that. So all this is what we solved, ignoring this. But now we made a logical conclusion that U prime, V prime are not small anymore. They're sizable. So therefore, the right-hand side is not 0 anymore. So what we need to do now is to go back and try solve the same problem without assuming that the right-hand side is 0. Is that clear? So that's what we will be doing now. Okay, so now let us see what it actually means. So let us look at just one example, one of the terms. So I chose to have this term, W prime multiplied by du prime by dz. So you can see where it comes from. We have all these terms, product terms in the right-hand sides, and I just picked one of them as an example. And see what happens if I start evaluating that. So if I multiply, so remember that my solution is in this form. Okay, it contains A times W times E plus complex conjugate. And the same thing can be said for U prime. So when you multiply them through, you will clearly see that this will multiply that. You will get A squared, right? You will get W, and you will get derivative of U. And each of them has E, so you will get E squared. See that? You also will have this multiplied by that, or by that, right? And if you take A and multiply it by complex conjugate of A, what do you get? Magnitude of a complex number, right? So square of that. So that's this, and there will be 2 of such terms. And finally, if you take this and multiply by that, you will get that. Agree? So, bottom line is that what you have here is terms proportional to A squared to A conjugate squared and to magnitude of A squared. 3 groups of terms. Agree? Okay. That's what you will have on the right-hand side. Do you have any of these terms on the left-hand side? Remember, A squared, A conjugate squared, or magnitude of A squared. So this will be proportional to A or A conjugate. This will be proportional to A or A conjugate. This will be proportional to A or A conjugate. None of them will have A squared or a magnitude of A squared. None of them. So therefore, you will have right-hand side which contains those terms, left-hand side which doesn't. We have a mismatch. We can't live with that, right? So right-hand side now drives the fact that left-hand side is inconsistent, right? So we started with the left-hand side, we solved left-hand side, and we computed the right-hand side. But now right-hand side says, okay, hang on. You need to match me. Now we have to go back and actually start modifying, start adding extra terms to my representation of so I need to start adding the terms to my initial assumption, what my solution looks like. So this is still my base flow, it is still there. This is still the linear terms, so linear eigenfunctions that we already know. It is still there. Complex conjugate is still there, but we need to have these terms and we need to have these terms. We have to keep adding. So we add this to the expansion. So because initially a was considered to be small and a squared was neglected, but not anymore. These have to be there. See? So it is very simple. So you have essentially a product of two sums, and you look at what appears in this product. What sort of combinations of A appear in this product. And then if you see anything new, you have to come back to the original expansion, essentially a representation of the original solution, and add them in. Is that clear? This principle of essentially sequential or stage-wise adding the terms. You add the terms as you need them. Okay? So that's really important. That will be the main procedure that we will follow for the rest of this subject. So that's how you do that. So you do something one step at a time. You see what happens, and then you come back and amend things, and then you repeat the iteration and amend thing, and then repeat iteration and amend, repeat, amend, and so on. Okay, so that's what is going to happen. Now, if I take these and substitute into equations, and I will have the different groups of terms, and those groups of terms will be distinguished by the presence of various powers of E and various powers of the amplitude. So, and they do not mix and match. Why? Because, for example, E squared is not the same as E. So therefore, E squared terms have to be considered completely differently, separately from E terms. Is that clear? Right? So literally, this means sine of alpha. This means sine of 2 alpha. They cannot balance each other because they are different. So therefore, you can only balance sine of alpha in their own world and sine of 2 alpha in its own world. Okay, so therefore, if we substitute this in, you should be able to separate the long sausage of terms that you will get, chop it into pieces, and all pieces must have exactly the same E and exactly the same power of amplitude. Is that clear? So again, it is very straightforward, maybe a little bit tedious, maybe a little bit confusing for, well, so some of you might, if you see it for the first time, might find it a little bit daunting, so too many details. But really, substitute, look, make a conclusion. One step at a time. No high science here, it's just substitution, substitute and see. So that's what you will have. And therefore, you will need to separate these terms. So, and obviously, if you have a squared multiplying the quantity, then time derivative will be of a squared. Right? A depends on time. And if it is present in the equation, and if you need to differentiate it, then you take a squared and differentiate the whole thing. Is that clear? Right? So therefore, that's what I will get then. So this group of terms is proportional to a squared. So we will see that this term will appear in my matrix equation on the left in exactly the same way as it appeared before, except you see there is no E term here. Why is it not there? Remember how it was obtained. It is this multiplied by complex conjugate of that. So this comes from this multiplying that. So you have A complex conjugate gives you magnitude squared. E multiplied E minus 1, cancellation, right? It is E to the power 0. That's why it is not there. Okay? So that's why you will get this. So therefore, remember my matrix Y contained alpha. Alpha is a part of E. E is not there. So therefore, it is equivalent to saying that alpha is equal to 0. Okay? This term, we have to take it as is. If it is A squared, and we need to differentiate it with respect to time, then it is dA squared by dt. So, and right-hand side will also be proportional to A squared, and we already know how it was going to look, so it will have something like that in the right-hand side. Obviously more terms than that, because we only consider a single one, so we will get more expressions like that. And that's what will go on the right-hand side. Is that clear structurally? So it is, if you do it by hand, then you probably will get a better feeling of that, but just try to get overall idea. Now, so overall, not necessarily nitty-gritty things, so, but the idea. So you substitute, you essentially have a product, you expand that product and see what terms appear, and then add them to the expansion, and then see what happens. So, any questions about what I've written here so far? So if we understand the first step, then after that we'll be doing essentially the same and the same and the same and the same, with very few variations. So is that clear? If it is not clear, let me know what exactly what the stumbling point is, and I will go through that once again. So really is important to understand this at this stage, because later on everything will be exactly the same. Okay. So next thing to consider is, can we do anything about that? We know that dA by dt is equal to sigma A. Remember that. We already know that. We concluded that previously. What about dA squared by dt? Well, just use the standard differentiation, right? So differentiating the square will give you this. So, but what is dA by dt, magnitude of dA by dt? Remember the solution, dA by dt is equal to sigma A. So A is equal to what? A is e to the power sigma t. And sigma consists of real and imaginary parts. So therefore, I'll do it once. And so remember, what I need to do is this. So I know that E is equal to, say, A0 e to the power sigma t. Okay, that's what my assumption is. Which is A0 e to the power sigma r plus I sigma I t. Agree? Which is equal to A0 e to the power sigma r multiplied by t multiplied by e to the power I sigma I t. Agree? Now, this is real term, right? because E is real constant, T is real time, sigma R is real part. So this is real. This is purely complex exponential. So now if I take the magnitude of that, I will get obviously magnitude of individual things. So it is magnitude of A0 e to the power sigma R T magnitude e to the power I sigma I T magnitude. Agree? So, which is equal to? Nothing we can do about that. Can we simplify this somehow? So what do we know about exponential function? Real exponential function. What are the value of real exponential function? What are they? How does exponential function behave? So where does it belong? What is the range of exponential function? So what does it produce? So domain of the definition is obviously all values of t, but range, it means what the possible values are. Positive, right? So if they are positives, therefore magnitude is not required. So therefore we'll simplify that. And what about the magnitude of a complex exponential? 1. So it is disappears. So therefore that's what we have. So the magnitude of A is essentially magnitude of A0, whatever that is, multiplied by just a real exponential function. Okay? So therefore if we differentiate this with respect to t, we will get, so the final thing I will add here is dA magnitude by dt is equal to A0 magnitude sigma to the power r, sigma r multiplied by e to the power sigma r t. Agree? So which of course is equal to simply sigma r multiplied by a itself, right? So you can see that. So it is A0 e to the power sigma RT, that's this, so therefore this is a magnitude of A. And the only thing is that we multiplied by sigma R. Is that clear? Okay, good. So, all right, now let's keep going. So that's exactly what I have here then. So therefore, instead of time derivative of a squared, I will simply get 2 sigma r. So differentiation of magnitude of r squared, or of a squared, gives me 2 sigma r. Not sigma, but 2 sigma r. Okay? That's what I have. So my equation will become like that. Or if I recollect what I introduced as a substitution for the left-hand side here, I will get the same matrix Y, but evaluated at alpha equals 0. I will have the same matrix X, but multiplied by 2 sigma R rather than sigma. So that's what I will have. I will have this new component that we would like to find, and I will have some right-hand side which comes from considering those products. So that's the system of equations that I will need to solve. I will still have 3 equations, but alpha will have to be substituted with 0, and sigma will have to be substituted with 2 sigma r. And instead of 0 on the right hand side, I have something like that. Okay? So can we solve this system of equations? So right hand side terms are written explicitly here, so you will be able to check that, and I'll just leave it for you as an exercise. So the question is, yes, we have these equations written in the matrix vector form. Can we solve this? Or in other words, can we invert this matrix? So this is a matrix, and solving it, this system of linear equations, means that we need to invert the matrix. Now, let's go back to the basics, linear algebra. When can we invert the matrix? It must not be singular, right? So what does it mean, singular matrix? Determinant is equal to 0. So determinant must not be equal to 0. So, and this is completely opposite to what we did at the linear stage, at the first stage. We had to make this the equation singular to be able to solve them, right? Now we need to insist that the equations are non-singular. So if equation is singular, its determinant is equal to 0. But how do we find eigenvalues? By doing what? If you have a matrix, how do we find the eigenvalues of the matrix? What do we need to do? What do we do? So if we have a matrix with eigenvalue included in it, how do you find it? What is the condition? What did we do before? So remember, simple example when we found sigma minus 3. So where did you find sigma from? Determinant, right? So we actually made the system singular by considering determinant and making it 0. So therefore, at linear stage, we intentionally try to make this matrix on the left singular. And here, we don't want that. We want to solve this equation, so therefore we would like to make sure that this is non-singular so that we can invert this matrix, and then we will simply get W20 is equal to inverse of L multiplied by F20. Right? So that's what we want. And for this, we need to make sure that this is not singular, which means determinant of this matrix is not equal to 0. And determinant is equal to 0 is associated with eigenvalues. If we stick eigenvalue in, then the matrix will become singular by definition. So this means logically that we need to check that 2 sigma r cannot possibly be an eigenvalue of matrix L. Is that clear logically? So we need to make sure that this is not an eigenvalue of the original matrix L. Now the question is, can we actually show that? And any idea? Yes or no? I don't ask you to actually show that. Just tell me, yes, what do you believe? Yes or no? Yes, yes, of course, otherwise I wouldn't talk about it. Yeah, use your logic. If I'm talking about it, why? Well, obviously I want to show it to you, right? So I'm just asking for applause, right? So essentially that's what people on stage do. So I'm performing in front of you. So your yes, it is sort of applause. All right, so let us go back a couple of pages. How much time do I have left? 6? Okay. To this picture. Remember how we chose this point. We chose this to be the maximum, right? For physical reasons, because this is the vampire, will pretty much eat everyone else. Right? So this is the one. So, and now we are talking about 2 sigma r. Where is 2 sigma r? It will be here. But we already know that the maximum possible eigenvalue is here. So, which means that if we choose the value above this point, which is, well, obviously that's what we're doing, it is double of that, then it is not an eigenvalue. That comes from this picture. Is that clear? Right? Because we are talking about 2 sigma r, but 2 sigma r is definitely greater above this point. And we know that this is the largest possible eigenvalue. So there isn't anything there. So therefore, we are fine. We can solve that system of equations. We're absolutely fine with solving that system of equations by simply inverting this matrix. And if we invert these metrics, we have the right-hand side, which is determined in terms of what we already know. Basically, we know all these terms here, right? We computed them, we plotted them, we know what they are. So therefore, if we compute the right-hand side, substitute them in the equation, invert these metrics, we have it. Obviously, we don't do it by hand. We will ask MATLAB to do that for us. Okay? And that's what I will do next after the break. So in the next lecture, I will simply show you the picture, what comes out of it. And I would ask you, if you guys have laptops with MATLAB installed on it, could you please bring it with you? And I will upload this code so that rather than trying to look at the screen, you look at your own computer and you will press the button and will play with it. Okay, so if you have that opportunity, please do that. So bring your laptops with you and we will make it sort of interactive, so sort of tutorial type in the second half of this, of today. Okay? All right, I'll see you in the afternoon. So.